Today we want to talk about ions. Ions are atoms or group of atoms that have a positive or negative charge because they've either lost or gained electrons in some kind of an electrochemical process. There are two different terms that we have to be familiar with. One is anion. An anion is an ion with a negative charge. Now remember, electrons are negative. So if something has a negative charge, it's because it has gained electrons due to a gain of electrons. Cations, on the other hand, are, remember, cats are positive. So cations are positive charges due to a loss of electrons. They're positive because they've lost some of those negative charges. So those are two terms that you're going to have to be familiar with. Now, there are some common ion charges that you can determine about an element when it's in the process of bonding with some other elements to form a compound. They'll form these common ion charges. And you can tell what they're going to be often based just on where they're located on the periodic table. Now I've got it in writing here, but what I want you to do is to get out your periodic table, the same one that you put all of your group names and things like that on when we were doing the periodic table notes last time. And let's flip a little bit through here and let's label this. Everything in group 1A, those alkali metals, up at the top, you'll want to label that those are going to be our +1 ions. I didn't write that very well. It pretty much just looks like a big splotch there. These are our +1 ions, everything in that group: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Those are our +1 ion elements. Everything in group 2A is going to form a +2. Now, when we get over to this next area, we're going to get some variations here, but we often get a +3 from our boron, aluminum, gallium, those elements that are bordering that staircase on down. Now, when we get into group 4A, those are a big, huge question mark. We're not sure what those are going to do at times. For our group 5A, -3 when they're in just simple compounds. That's the charge that they're going to form. And these will work down to the staircase. This staircase is kind of a barrier for those charges. In some instances, it'll go past that staircase, but that's pretty much where we're going to draw our barrier line. Group 6A is going to be -2, 7A -1, and the elements on the end, those noble gases, those don't form compounds. We're going to give them a big 0 for forming ions. They don't form ions. They don't react pretty much with anything. So those are our representative elements. Now here in the middle, this whole middle is mostly our C, what we call I often call the sea of unknown charge. So this sea of unknown charge down here kind of extends all the way through here and on down. Again, I call it a sea of unknown charge. But there are a few little islands in there that we need to know. Now, when we don't know the charge, we're going to see in a little bit that we name these ions a little bit differently. So it's important for us to know whether they are an unknown charge or not. There are 4 elements over here in this area that we are going to know the charge on. Aluminum, even though it's past the staircase, is still going to get a +3 charge. Zinc is an always +2 charge. These are what I call my always trues. They will always get this particular charge in nature. That's all you'll ever find them when they have a charge. Cadmium is also +2. Silver over here is +1. I strongly suggest that you write those positive charges in on your periodic table. Kind of an island, those islands in the midst of a sea of unknown charge. So all down through here, we don't know anything about them, but since much as far as charge is concerned, but we do know they're positive something. If they are metals, when they bond, they're going to lose electrons, and when they lose electrons, they're going to form that positive charge. So that's what I want you to write down. We're going to be referring back and forth to this. I'm not going to keep flipping back and forth to it over and over again, but I want you to keep it handy so you can look these things up and see what I'm talking about when we find these charges. So let's go back to our notes. And one of the things that we want to be able to do is to look at an element and decide what its common ion is, the ion charge that it forms is going to be. Bromine, if you remember bromine, look at your periodic table. It's over in group 7A, and at the top of bromine's column, there's a -1. What that means is that bromine, when it forms an ion, is commonly going to form a -1 charged ion. Now, we don't put ones in formulas or charges, so I'm just going to put a negative there without the 1. So that's a common ion it forms. Calcium, if you'll look for calcium, Ca, it's in group 2A, number 20. Since it's in group 2A, it has a 2 plus up at the top of the column. When we write the charge as part of an ion symbol, we write the 2 first, the plus second. So this is what it's going to look like when we show that charge for the calcium ion. Nitrogen, looking over number 7, nitrogen over to the right, you'll notice it's in the column that has a -3. And that -3 there tells us that the common ion formed by nitrogen is a 3 negative compound, the number first, the negative second. So I'm going to skip over there real quick and we'll look at all 3 of these. Here's calcium right here. Notice it's in that +2 column. That's how we know. Then we've got our bromine over here in the -1 column. So that's how we know it's going to form that Br minus. And so finally our nitrogen here, right here in the -3 column, that's how we know the common ion form for it is a -3. So that's where we're getting that information. The next thing it wants to know is the number of electrons that it loses or gains, and also how many electrons it will have total as an ion. Now, I'm not going to flip back here, but make sure you pay attention to the fact that calcium has 20 electrons when it's neutral, 20 protons, so 20 electrons when it's neutral. Nitrogen has 7 electrons when it's neutral, and bromine has 35 electrons when it's neutral. That's going to be important to us in just a moment. So let's look back here. If it's a -1 charge, remember those electrons are negative. So that means it must have an extra electron floating around in there somewhere. So it must have gained 1 electron. Calcium, over on the other hand, with its +2 charge, it must have lost 2 electrons because those negative charges must have gone away to leave that as a positive ion. So calcium has lost 2 electrons. Nitrogen, with its 3 negative charge, what must have happened to it? It must have gained 3 electrons in order to have that charge. Now let's think again. I just showed you how many electrons they have when they are neutral. So I'm going to make a little column over here for when it's neutral. Remember we said bromine had 35 electrons when it was neutral, calcium had 20 electrons when it was neutral, and nitrogen had 7 electrons when it was neutral. But now we just said that bromine gained an electron. If that's true, then the number of electrons in the bromide ion must be 36 electrons. Calcium, on the other hand, although it started out with 20 when it was neutral, it now says when it forms the ion, it has lost 2 electrons. So evidently now it has 18 electrons when it's an ion. Nitrogen as an ion, well, at first when it was neutral, it had 7, but now it says it has gained 3 electrons. Evidently now, as an ion, nitrogen has 10 electrons. So that's how you find that information, the number of electrons that are present in the ion. It's all depending on what its charge is and how many electrons it had when it was neutral. Now in this next part, we're going to name the ions. This is going to be our introduction into naming compounds in the next couple of days. If we have a metal from group 1A or 2A, they're named as is. They are our known charges. There are others that are named as is as well. Silver, cadmium, zinc, and aluminum are all known charges. We don't have to worry about specifying what their charges are. They do not need any Roman numerals. Roman numerals are what we use to show the charge on our sea of unknown charge elements. So if we have metals outside of groups 1A and 2A and metals that are not part of this, then they are going to need a Roman numeral corresponding to their charge. So those are going to be our most difficult ones to name, and we're going to look at that in just a moment. Negative ions, all we have to do to a negative ion is change its ending to an IDE. We'll talk about the polyatomic ions in just a moment, but let's name those and write formulas for those elements really quick that are single atomed elements. Br minus, for instance. Since it's negative, looking back up at your rule, you'll see that all you have to do is change the ending to IDE. So bromine becomes bromide. Always remember to put the word ion after it. You see another single atomed negative element. Looks like we've got P3 minus here. At first, you might think it's phosphoride, but most of the time, not always, but most of the time, they take just the first syllable. So this becomes phosphide. So you get things like, instead of nitrogenide, you get nitride, and carbide for carbon, and oxide for oxygen. Some of the ones will be familiar because I've really introduced you all the way through this first part of the year with consistently hearing compound names over and over again, so some of these names will seem familiar. So those are our negative ones. The negative ones are our easiest ones to name. Again, you just change the ending to IDE. So now let's look at the positive ones. When we see Mg2 plus, Fe3 plus, all of these positive single atom elements, we have to decide if they need Roman numerals or not. Now remember, if they are in a known area, known charge area of the periodic table, then they're not going to need Roman numerals. So let's glance at our periodic table again. This group, 1A, this group, 2A, those positive ones, we're going to know what their charge is. Aluminum is an always true. Zinc, cadmium, silver, those are always trues. They will not need Roman numerals. Our sea of unknown charge, these are the elements that need Roman numerals. Our sea of unknown charge, these elements need Roman numerals. So let's go back now and look at magnesium. If you find magnesium, you'll see that magnesium is in group 2A. It has an always true +2 with it. It is, since it is in a known charge area of the periodic table, we can just name it as is. All we have to write is magnesium ion. Do you see another element, single atom element or ion here that is in the known charge area of the periodic table? Well, hopefully you recognize Ag, silver, as being one of our always trues, as being one of our little islands of charge in the midst of our transition elements. So silver is another one that does not need a Roman numeral. All we have to do is write the name and put ion after it. Now our other two elements here, our other two monoatomic or single atomed ions here, are both part of the sea of unknown charge. If you look them up on your periodic table, you'll see that they're right in the middle of the sea of unknown charge. Since they are, they have to have Roman numerals. And the Roman numeral is going to be the charge. Now you have to know your Roman numerals. I've never seen Roman numerals go past, well, really the highest you're going to see a Roman numeral is a 6. I've never seen it go past 6. So 1, 2, 3, 4 is IV, 5, 6 is VI. I'll go ahead and we've looked at these Roman numerals when we were writing them up for our group numbers. 7 is VII. It's not going to go up this high, but I'm just going to put them all up here again for us to practice them again. And there's 8 VIII. So those are the ones that you're going to need to know. Primarily for this application, really just up to 6, just 1 through 6. So iron, since it has a 3 plus charge, is going to be the iron 3 ion. And lead, since it has a +4 charge, is going to be the lead 4 ion. Please do not put regular numbers. They must be Roman numerals. Now the next two, SO42- and OH-, hopefully you'll recognize them as being different. The fact that these are what we call polyatomic ions. We're doing flashcards dealing with these polyatomic ions. And as soon as you see more than one element or one atom present in that ion, you know it's not a normal one. You know you have to look on the list. So these are polyatomic. They have more than one atom in them. So find the list. And the list is back here. We need SO4 2-, and we see that SO4 2- is right here, and that's sulfate. The other one was OH-, and OH- is right here. It's hydroxide. So let's fill those in. This is the sulfate ion. Remember, if it's polyatomic, you're going to check the list. Sulfate ion, and OH- is the hydroxide ion. Now you want to look for these. It's easy to see them and pick them out when they are in the formula form, because you can see that there's obviously 2 capital letters, so there's 2 different elements in there. So they're easy to pick out. Not so easy when they are in the word form, the name form. So you have to realize that if they end in ate or ite, it means they have oxygen in them, for one thing. Ate and ite, they both have oxygen in them, and they are polyatomic ions. If they end in ate or ite, they are a polyatomic ion 100% of the time. The first part of the name will be corresponding to the other element that's in there with it. There are 3, however, that we have to watch out for that do not end in ate or ite, and I'm going to show you those here. The 3 that we have to watch out for are ammonium, does not end in ate or ite. Notice all the rest of these are ending in ate or ite. Let's look at a couple more. We've already seen hydroxide. It does not end in ate or ite. We have to watch for it. And the other one's right above it, cyanide. Those 3 will catch us unaware if we don't watch for them. Everything else, it's very obvious. Ate, ite, ate, 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 ite, ate. All of them end in ate or ite. And they're, again, easy to recognize. Notice something else when you're studying for this polyatomic ion quiz, that if you know all of the ate forms, the ite forms simply have 1 less oxygen. Look at nitrate. Nitrate is NO3. Nitrogen, oxygen means that that 8 stands for oxygen. You have to memorize the 3, you have to memorize the negative charge for nitrate. But if you know nitrate, nitrite is identical in formula and charge. It simply has 1 less oxygen than its 8 form. And that's going to happen multiple times in these. Look at phosphate and phosphite, sulfate and sulfite. It happens nitrate, nitrite, etc. So watch for those. So let's go back here now. And if we have strontium, copper 2, those are our single atomed elements. Strontium is in group 2A. Since it's in group 2A, we've already looked at the fact that those elements are simply going to have a 2 plus charge. Copper 2, really nice, it gave us the Roman numeral. We wouldn't have known copper's charge otherwise because it's one of our sea of unknown charge elements. But since it told us that it was a Roman numeral 2, we know it's got a 2 plus charge. It's always positive. Carbonate. I'm hoping from our previous discussion that 8 just stands out at you. I would underline all the 8s and ites anytime I saw them so we wouldn't forget. Carbonate, if you look on your next page, see if you can find it real quick. Without looking it up, though, you should be able to get that it has carbon and the 8 stands for oxygen, so you should be able to find at least that much. When you look it up, then you'll see that there are 3 oxygens and that overall it has a 2 negative charge. Finally, ammonium is one of our elements that we have to recognize as being, outside of the box. It's not going to end in 8 or ite. It's one of the ones on our polyatomic ion list we just marked that it does not end in 8 or ite, but it is a polyatomic ion. And if you look on that page, you'll see that ammonium is NH4 with a +1 charge.